answering is at least as old as logic programming in Prolog and the method of resolution. As in Prolog, we have a dataset D, which is a collection of facts which are ground atoms. In this example, we know that John is a parent of Sasha, that Sasha is a parent of N, that John is male, N is female, but we don't know Sasha's gender. We also have an ontology O, a set of sentences from some fragments of fixed point first-order logic. The original Prolog, these sentences had to be Horn rules, but real-world ontologies often have disjunctive axioms like this one, which says that each person is either male or female. Then we have a conjunctive query Q, which is an existentially quantified set of atoms. In this example, the query asks if the data set necessarily contains a father and a daughter. Now, our task is to understand if Q is logically entailed by D and O. That is, if Q holds in all interpretations for D and O. So we consider D1, in which Sasha is male, and see that Q holds under assignment X goes to Sasha and Y goes to N. In D2, where Sasha is female, Q holds under assignment X goes to John, Y goes to Sasha. So we deduce that Q is entailed by D and O. This example illustrates that if we fix Q and O and join them into a single ontology-mediated query, capital Q, but vary the set of facts, then capital Q holds on those and only those datasets which have a parent path over person, leading from male to female. Thus, this reachability query is a rewriting of capital Q. Note that this query can be expressed in linear data log and is complete for NL. So we can say that the data complexity of this particular ontology-mediated query is NL. And we can answer this ontology-mediated query efficiently, provided that the data is stored in a system which supports this type of reachability queries, for example, a graph database. It is also easy to come up with ontology-mediated queries with data complexities AC0, L, P, and Co and P. This example highlights two fundamental problems of ontology-based query answering. The first problem is how to determine the data complexity of answering a given ontology-mediated query OQ with an expressive ontology O and a Boolean conjunctive query Q. That is, we fix O and Q and need to tell what is the complexity of decided entailments of Q over O and D in terms of the size of D. The second problem is to recognize which ontology-mediated queries are first-order rewritable, or linear data log rewritable, or data log rewritable. If this was possible, then given user requirements in terms of a list of ontology-mediated queries that should be answered by an information system, one could estimate its viability and produce requirements for the data storage units. Also, the correspondence between expressibility and complexity for a class of ontology-mediated queries would be a nice theoretical result. These two fundamental problems have been a hot topic of research since late 80s. In particular, boundedness or first-order rewritability of data log programs is their partial case. Note that the boundedness problem is 2x time complete for monadic data log and undecidable in general. Similar is the problem of linearizability. Is it possible to transform a given program into an equivalent linear program, which has at most one IDB in a rule body? In 2016, an interesting sufficient condition for data log rewritability of disjunctive data log called mappability was suggested by Grau, Kaminsky, and Nenov. Another line of research deals with how to classify patterns of constraint satisfaction problems according to their data complexity. Inspired the recent solution to the Federvardi conjecture on P-Co and P-dichotomy, there is no transparent criteria for simpler classes like L or NL. Also, criteria are often stated in terms of existence of certain polymorphisms, and there is almost no software which can check these conditions, with the notable exception of Pollyanna developed in Oxford, which runs out of memory on patterns with as little as 5 elements. Exploiting a reduction of ontology-mediated queries to constraint satisfaction problems, Bienvenu, Tenkate, Lutz, and Volter obtained an X-time algorithm for deciding first-order and data log rewritability of OMQs with shoe ontologies and atomic queries. Another remarkable result in this area is the AC0 NLP and P trichotomy for data complexity for L ontologies and conjunctive queries, which can be checked in X time. Now let's slowly turn to our contribution. We decided to strip this problem to the bare bones and consider ontology consisting of a single covering axiom. We considered 2 options: the classical covering axiom A implies F or T, saying that A is covered by the union of F and T, such as every animal is male or female, and also so-called universal covering, everything is covered by F and T. Together with each of these axioms, we may either assume that F and T are disjoint, or that alternatively we can assume that there can be objects which satisfy both of disjunctive concepts F and T. So we fix an ontology consisting of a single covering axiom and want to classify all conjunctive queries according to their data complexity with respect to this simplest possible non-Horn ontology. It is easy to come up with examples for each of 5 complexity classes: AC0, L, NL, P, and CoNP. This is the father and daughter query from the very first slide. And it should be clear that all queries with a single T and a single F are in NL. However, if the part between T and F is symmetric, then the complexity drops to L. If one of disjunctive concepts does not occur in Q, then the covering axiom doesn't contribute, and the query is first-order rewritable. If there are 2 T's and 1 F, then the query is usually p-hard, but some queries are in NL. For example, if you swap this T and this F, you get NL. And if each of disjunctive concepts occurs twice, then the query is usually CoNP-hard, but it is unclear if this is always so or not. So you can see that our naive idea to classify queries according to the number of occurrences of disjunctive concepts needs some refinement. Now let's get slightly technical. Note that there are 2 ways how disjunctive predicates can occur in a conjunctive query. An occurrence of F in Q is solitary if the second disjunctive predicate T does not occur at X. A solitary occurrence of T is defined similarly. It can also happen that Q has both disjunctive predicates T and F at the same point. Such occurrences are called twins. Of course, this option can be ruled out by assuming the disjointness condition. It turns out that it is much harder to classify queries with twins than queries with only solitary occurrences of disjunctive predicates. For example, one can show that all twinless queries with at least one solitary occurrence of each of disjunctive predicates are L-hard, which gives us a nice criterion of first-order rewritability for the usual covering axiom with disjointness condition. On the other hand, if we assume that Q may have twins, then the problem of first-order rewritability becomes p-space hard and highly likely even 2x time hard. So in our main result, we assume disjointness of the disjunctive concepts, and also, like Foto Afrati in her paper on the determinacy of conjunctive queries, we assume that the binary atoms of our query are arranged into a directed path. Under these conditions, we have the following syntactic tetrachotomy theorem. The query is in AC0 if and only if one of the disjunctive queries does not occur in it. The query is NL complete if and only if one of the disjunctive predicates occurs once, and the query is in some sense periodic. For example, this query is periodic, and this is not, because the places 0, 1, 2, on which f and t's are in this query, form an arithmetic progression, and 0, 1, 3, on which t's and f are here, don't form an arithmetic progression. The queries which have t's on both sides of f are not periodic by the definition. The query is p-complete if and only if one of the disjunctive predicates occurs once and the query is not periodic. And so the query is co and p-hard if both disjunctive predicates occur at least twice. Note that the proof of co and p-hardness is rather involved, even if it is easy to show that some particular queries with this property are NP-hard by considering gadgets for variables and clauses of a conjunctive normal form. We had to analyze many cases before we proved that this construction can be carried out for each query in question. This is it. Now it is time for questions.